Hello and welcome to the AI Research Roundup. I'm your host Alex, and today we're diving into some fascinating work in large language models. The paper we're looking at is titled Byte Latent Transformer Patches Scale Better Than Tokens. Essentially, the researchers introduce a new architecture called BLT that works directly on raw bytes instead of tokens. The big news is that they show it can match the performance of traditional token-based models, but with better inference efficiency and robustness. A key idea is using dynamically sized patches of bytes, which adapt based on how complex the data is. So Figure 1 really illustrates this scaling advantage, particularly for fixed inference costs. What we're seeing here are plots comparing BLT models, the orange lines using entropy patching, against Llama BPE models in blue. The axes show bits per byte versus training flops. Lower bits per byte is better. Notice how the BLT lines, especially the one with the larger patch size 8, trend downwards more steeply. They actually overtake the Llama models as training progresses, showing better scaling. This highlights how BLT lets you trade model size and patch size for better performance at the same inference budget. Right? So building on those scaling results, Figure 2 actually shows us the BLT architecture itself. It's got three main modules working together. There's a lightweight local encoder that takes the input bytes and uses things like cross-attention and, well, that entropy idea we mentioned to group them into patches. Then the core is a large latent transformer that processes these patch representations. And finally, a local decoder translates those patch predictions back into the final byte sequence, again using cross-attention. This structure enables that efficient patching. Okay. So, thinking about that architecture we just saw, specifically the entropy patching idea used in the local encoder, Figure 4 really zooms in on how that works. What we're looking at here is the entropy calculated for each byte in a sample sentence. You can see the blue line goes up and down, representing how predictable the next byte is. When that entropy value jumps above the threshold, that horizontal red line, well, that basically tells the model, okay, start a new patch here. You can see the vertical gray lines marking those patch starts. This really highlights how the patches are dynamic. They change size depending on the data's complexity. Building on that idea of entropy patching we just saw in Figure 4, Figure 3 actually compares it visually to several other ways of creating patches from bytes. You can see the same sentence, Daenerys Targaryen, is broken down differently by each method. There's fixed 4, strided patching, the familiar BPE tokenization, the entropy method we discussed, plus variations like entropy with monotonicity, space patching, and even a CNN-based one. This really shows how the choice of patching scheme directly changes the resulting patch sizes and, well, the number of patches, which affects the overall compute. Okay, so looking closer at how those patches are actually processed. Figure 5 gives us a more detailed view of the local encoder and decoder modules we saw back in Figure 2. The key thing here is the use of patch cross-attention. In the encoder on the left, you see it takes the byte embeddings and uses them as keys and values, while the patch representations act as queries. This is how it pulls the byte information into those patch representations. Then, well, the decoder on the right does something similar but reverses the roles. The byte representations become the queries, and the patch representations are the keys and values, effectively mapping the patch information back to the byte level. Okay, so we just dove into the details of that cross-attention in the local encoder and decoder. Well, Figure 6 kind of brings it back to the bigger picture, showing the scaling trends for BLT models with different architectural choices compared to standard token-based models. Looking at the left plot first, this focuses on space patching. The red square line is BLT space patch size 6. And interestingly, the red circle just below it shows the same model without cross-attention. So you can see removing that cross-attention we just talked about. Well, it does hurt performance a bit compared to the version with it, especially when you look at the Llama 3 BPE baseline in blue. It also compares against some other byte models here too. Then, the plot on the right should look somewhat familiar. It's showing scaling for entropy patching, similar to what we saw in Figure 1. Again, we have bits per byte versus training flops, we see BLT entropy models in red, with patch sizes 4 and 8, compared against Llama BPE models in blue. The new thing here is that it explicitly includes Llama 3 BPE as a baseline, and also compares against another byte model family called Megabyte++, shown in orange. And the takeaway is consistent. BLT performs comparably and scales well, especially that patch size 8 version, against these strong baselines. Okay, so those scaling plots give us the trends, and Table 1 here shows actual downstream task performance for FLOP matched 8 billion parameter models. We see Llama 3 compared to BLT space and BLT entropy patching. Looking at the average scores at the bottom, BLT entropy actually edges out Llama 3, 61.1 versus 60.0. BLT space is a bit lower at 58.0, but notice its average patch size is much larger, 6.1 bytes compared to around 4.5 for the others. So this really shows BLT entropy is competitive or better, while BLT space trades a little performance for potentially better inference efficiency thanks to those bigger patches. So wrapping things up on the Byte Latent Transformer, the key takeaway really is that this patching approach, especially BLT entropy, is proving to be really competitive, even matching or slightly beating strong models like Llama 3 on benchmarks. It suggests that maybe we don't always need traditional tokenizers, and processing bytes more directly is a viable path. This kind of work is important because it pushes towards potentially more efficient and fundamental ways of handling language. Well, that's all for this episode of the AI Research Roundup. Thanks for tuning in. I'm your host, Alex.